All right, we're going to do some drawing. This is going to be a two-part video. This is part B. The other one, part A, is more complicated. So part B should be the first one. I should probably rename those. It's really stupid. But anyway, this is part B. All right. First of all, in the Glade window, we've got the usual window, we've got fixed, and we've got draw. It's an instance of GTK drawing area, as you can see here. And it comes from display and drawing area, and I dragged it in. All right. In drawing area, I've given it a name. It's called draw 1. It's located at 0, 0. It's upper left-hand corner. And then its size is down here, 440 by 261. So 440 wide, 261 down. There's some margins I was playing around with. They don't do much of anything, but they're there. Okay, only one signal. The signal is draw. Where is it? There it is, right there. Draw. On draw 1, draw. That's the function that will be called whenever it needs to draw the area. It'll be initialized the first time you start the program, and then it'll be called periodically to update. Okay, and then I've got a label. It's just a plain old label. I didn't even give it a name because I don't change it or anything. And it's got the content CPU utilization. Okay, so that's all there is there. Not much of anything different. Just this guy, the draw, which is empty now, and one callback. All right, get that off the screen. The program down here is fairly short, as it turns out. First of all, I declare a timer handler, which I'm going to have a timer that's going to click every second, and every second the timer is going to look up the current CPU utilization, and it's going to put it into an array and shove everything in the array down. It'll put it in the first part of the array, and everybody else will be shoved down. Not the most efficient, but it works. There's the array, 100 elements, CPU. I use CPU utilization as a calculation. It doesn't need to be global. There's the on destroy, which gets me out. So what do we got? First of all, we initialize the array to be all zeros. So the CPU utilization, because we start off with a flat line, 0. Okay, this is the same as before. Initializing GTK, starting the builder, it's part1.glade file, getting the window, connecting the destroy, the callback signal to destroy the window, that's on destroy. And you probably can put that in the Glade, but nonetheless, I've done it here. And getting the signals for fixed, although I don't actually use it, and draw 1. Draw 1 is the object that is the drawing area that we're going to draw in. Unref the builder for tidiness purpose, not much else. Keep above, that's optional, has nothing to do with drawing. Show the window, start the timer. Starts the timer. It's going to be 1 second between clicks in the timer. And we pass to the function the name of the function that will be called once a second. And it's called timer handler. And I'm not passing anything to it. Timer handler will get nothing, just null. And I start off the main GTK loop, and that'll keep running. Okay, there's the on destroy, which you've seen before. And first of all, the timer handler. Fairly simple. I've got some static variables here. Some static variables which are going to hold the we're going to contain the time, times that will from one time to the next. We get the previous time, the current time. The time that we're going to get is an accumulated time. So I want to difference the current time from the previous one to know how much was used in the meantime, as it were, utilization in the meantime. And it's in hundredths of a second. So it actually, it corresponds well to a percentage. And there's a flag indicating whether I've done this once or not. The first time through, we just initialize. I've got 2 character strings. Okay, how do I get the time? How do I get the utilization? Well, in /proc/stat, there are a bunch of lines. Here, I'll show them over here. Thank you. Yeah, bunch of lines, as I said, which gives information about the CPU and other stuff. The first line is the aggregate for the CPU. Now, my machine is an 8-core machine. Then it gives you the individual numbers for each of the individual CPUs. And you can look up what these numbers mean. But the first one is the accumulated amount of time since boot that's been used by, this is all of them aggregated together, and these are the individual CPUs. So what I'm doing over here is saying head-1, which means the first line. This line right here is the only one that's going to be echoed of /proc/stat. So that program head will write out the first line of /proc/stat. And I'm doing it in a popen, which is like a system call. It starts a shell. But the output of the shell comes back to me. In this case, it comes back because of the R, because I'm going to read from the shell. W would mean I was writing to the shell. But anyway, it's going to come back as an input line coming in through the file pointer P1. Okay. So we open P1. I assume it works. I mean, it's time to see how it couldn't work. And technically, I should check to see if P1 is null. But anyway, I really think /proc/stat is going to be there. All right, I read the line in from the, and I do an scanf, and I ignore the first thing, which says CPU. The first text over here, as you notice, that CPU, that's character strings. I ignore them, and then I'm over here. And then I read in the time, okay, into time 2. So I really want the time 2. I don't care about the word CPU. I close out the file pointer, and I just add an extra line. If the flag is 0, then I turn the flag on, I copy time 2 into time 1, here's where the difference is, and I return true, is the boolean, and the true means no further processing on this timer interrupt. False would mean, yeah, you can process it further, but there's nothing else to be done. So that basically sets my base time. Subsequently, it's going to be differences, as you can see here. If flag is 1, which would be the second time down, and all subsequent times, CPU utilization is going to be time 2 minus time 1. That's the difference between the two clicks, and we're doing this once every second. So that'll be basically, that's the amount of CPU time that was used in the interim. Now the CPU time, if one of the CPUs is at 100%, that will come back as 100. All right, I think it's 100. Yeah, is it? Yes. It's it's supposed to be in hundredths. It's in hundredths of a second. So if one CPU is in full utilization, it'll be 1 at 100. 2 would be 200, 300, 400, and so forth, up to 800. Okay, here's where I shift the CPU values. Start at the top and shift them all upwards. Therefore, leaving at CPU sub 0, index position 0, an empty spot. And I put into the empty spot the utilization divided by 8. So it's not going to go from 0 to 800. It's going to go from 0 to 100, which would be the actual utilization that goes into them. So the array is going to have the most recent 100 observations. And when we paint the screen, we got to paint the whole screen. We don't only paint part of it, so we're going to paint all 100 of them. Okay, CPU 0, that's in the lowest position, and I print it out. You'll see the numbers coming out on the screen as I'm doing this, and it's technically it's a percentage. So if all 8 CPUs are in usage, CPU utilization will be 800, and divided by 8, it'll be 100, which is 100%. Okay, so you'll see that there. I copy time 2 into time 1, and I run this function which tells the GTK, hey, why don't we draw something? Trigger a draw event on the widget draw1. So the background loop, the GTK loop, will queue up a draw event for widget draw1. And since there's nothing else going on, that's going to happen immediately. So that'll trigger that signal. And then I return true. I'm out of the timer. The draw signal is down here. This is draw one, draw. This is the signal. This receives the signal whenever there's a draw event. You'll get one immediately when the program starts up, and that'll basically clear the screen. Let's see, height and width. These are in here. I'm not using them, but I thought I'd leave them here. This gives you the height and width of the draw window. I'm not using them, but I just left them in there in case you want to find out what they are. So there's the... Now the drawing is all done in Cairo, which is a separate package of drawing stuff. I'm not very good at it. There's a lot in it. There's a lot of functions. You can draw arcs and rectangles and squares and straight lines. All I'm doing is drawing lines. You can fill things in. You can change colors. It's actually not that complicated. But so if you really want to get into drawing, you're going to have to look at the Cairo functions. Well, the first Cairo function is to set the width. CR. When I came in here on the draw function, I got a pointer to the Cairo surface in the drawing window, all right? And that's the thing I play with. So I call the Cairo set line width, and I pass down CR, which is the pointer for this drawing surface, and I'm setting it to 1.0, a width of 1.0. It doesn't appear to be 1 pixel. It's 1 unit of some kind. I don't know what it is. It looks like it's thicker than a pixel. Considerably thicker, but whatever the window what the units are, I don't know. I could look it up, but I'm sure the function would tell you what the units are. Then I go. Now I'm going to start. The window is clean. It's empty. I'm going to start drawing on it, and I'm going to draw all 100 elements of the CPU array. So I start off from 0 up to 98. Okay, I draw all but the last one. Well, I go from 0 to 98 because you need 2 points. You need the current point and you need the point to go to, as we'll see in a second. First of all, I set the color. Suppose I could take this out of the loop. The color is red, green, blue. It's between 0 and 1. And you see I've got red at 1. If you want other colors, blend them as appropriate. It's red, green, blue, and it's a double precision floating point number, so potentially you've got a lot of colors. All right. First of all, I move the imaginary pointer to a place on the screen. Now, I'm kind of adjusting this. First of all, it's got to be a double, so that they're all being cast. All right, so it's when I just printed them out or drew them normally, they were too close together, so I'm using multipliers to expand things without exceeding the bounds. So it's x by y, by the way. The first parameter here is x. I'm in the x parameter. So I is going to be the horizontal. So I'm starting at the leftmost part from, I being 0, 1, 2, 3. It's the left, next to the left, next going right. So I times 4. So in other words, the maximum would be about 400 wide. When we get up all the way up the top. And if you remember, the window is 440 or something like that. I don't. And then so it's I times 4, and I displace it by 10. Okay, so instead of starting at the actual left edge, it's in by 10 pixels. But it's expanded by a factor of 4. So that's where we start the draw. And then in terms of the vertical, again, it's double precision. This is the vertical. Well, first of all, it's 100 minus the value in CPU sub I. We're not drawing at the top of the screen. We want to draw down near the bottom of the screen. That's 0. That's our 0 position. And if CPU utilization goes up, we want the line to move up. So if CPU utilization is 0, we will be at 200. Got it? So if CPU is 0, my starting point for the draw operation. I got 2 points here: the starting point and the connecting point. The next line is the connecting point. Draw 2 from 2. This is the from. I'm setting up the starting point. So so if CPU utilization is 0, this will be 100. The value of this expression will be 100 times 2. In other words, it'll be 200. It'll be down 200 from the top. That's my baseline. The actual window is greater than 200, as you may recall. And again, I displace it by 10. So that's the starting point. The second point is the same idea, different function. A Cairo line 2. So from starting at this point, we move to this point. This is where the line actually gets drawn. So it's the same thing. It's we're in the same horizontal location. We didn't change. No, excuse me. Horizontal location I plus 1. Okay, we horizontally have displaced by 1, which is multiplied by 4. So it's actually 4, displacement of 4. Up above here it was I. Now it's I plus 1 because the CPU value is going to be I plus 1. So the most recent one, the one that starts off at CPU 0, will be the leftmost one. The second one will be 4 in from it. The third one will be 8 in from it, and so forth. Because of the multipliers by 4, it's actually 1, 2, 3. All right, messy, but not that really tricky. This guy here is pretty much the same thing. The only difference is that we're not doing CPU I, we're doing CPU I plus 1. So we're drawing from that position to this position. And again, it's just placed by 10. All right, so that connected a line from the, let us say, the leftmost to the second leftmost, or from the second leftmost to the third leftmost, and so forth. All right, and then we stroke it. This actually puts it on the screen. You have to do it for each one, apparently. And we're done. So basically, we draw 100 segments. And we only go up to 98 because 99 is the last one. And, of course, I plus 1 here is that'll be 98 plus 1. That's 99. That's the last element. So that's all there is to it on the fact of all this gymnastics about, shifting things on the screen. These are just points. And so I'm using the I. I'm using the I as the x-axis. And as I goes greater, it's time into the past. I0 is the current, the most recent one that was added to the array, because the array is just being shifted upwards every time I add one to it, which is once a second. And the vertical is based on the value in CPU from 100, and then multiplied by 2. So a value of 0 CPU gives us the maximum displacement from the top down. Anyway, does this work? Of course it works. All right. And here we go. And you can see some little bumps going on. CPU utilization, there's my label. And this is, like 200 down. Over here, you'll see the numbers popping in. And surprised there's anything going on, as a matter of fact. One of the CPUs is actually doing something. Who knows what? Probably could be doing some background maintenance of some kind. But there's my utilization. It's only one CPU that's doing it. Otherwise, we'd see a bigger number. Up here, what I had done here is to I can run some programs in the background. This is a mumps program, and I'm running it with the ampersand, which means it's going to kick off, and I'll get control again. Now you see the CPU jumped up to 170%, 178. I can run another one. And now we're up to 200. Keep running them. And you can see it's doing it. Now I'm up around 652. I don't know what's going in the background. That's this program is not using that much. It's not using hardly any CPU time. So something else is going on in the background of the machine. I don't see what. I don't think there's anything that I can see. Oh, it's OBS, of course. OBS is running to record this. I hope OBS is recording us. All right, they kicked off another one. Now I'm up to 733. Let's kick off another one, and we're max out now. Well, I guess we've gotten as maxy as we're going to get, given all things being equal. And I can actually hear the fan spinning up because the temperature, if you look down there someplace, you can see the temperature. Fan spinning up, the temperature is beginning to rise. Temperature's at 65 and the fan is trying to catch up with it. So there it is. Now if I kill these guys, you see it drops way the hell down. And the only thing that stays running, of course, is the OBS, which is using about 70-ish or so percent of the CPU. So what have we got? Well, we've got the ability to draw graphs. You could fill this in, you could change colors, you could do all sorts of stuff. It's actually fairly easy. You'll have to look at the Cairo functions. But once you get the Cairo functions, it's not hard to generate an area on your screen with some kind of dynamic graphic activity. And there you are. I've got the second video, which is a paint program, and that's more complicated, and it's far more parts to it. So I will quit it now.